Welcome to Brilliant Academy. In today's class, you are going to learn how to derive the equation of torsion. We have that the equation of torsion is given as T all over, this is torque all over the polar moment of the shaft equals to modulus of rigidity, which is modulus of rigidity of the shaft multiplied by the angle of twist all over the length, and is equals to the shear stress all over the radius of the shaft. So how did we arrive at this equation to be the equation of torsion? I'm quickly going to use the diagram I have here. We assume that this diagram is a shaft. So this is a cylindrical shaft, a circular shaft. And quickly, let me introduce the parameters that we are going to be using in our course of analyzing how to get the torsion equation. So we have tau here as the shear stress and r as the radius of the shaft, and g as modulus of rigidity, and theta as the angle of twist, and phi as the shear strain. Also, we have T as torque, and this is the polar moment of the shaft, and L is the length of the shaft. So quickly, before you attempt deriving the equation of torsion, I want you to note down three things. Note down these three key ideas, because it's going to help you, it's going to guide you while you derive the equation of torsion. So, looking at this triangle, you analyze this place first. That's the first thing you are. If you look at this point here relates to this angle, and at the same time it relates to this angle. So when you analyze this angle, you get some useful information. You analyze this angle, you get some other information. With knowing that this part and this part relate to each other, you equate what you have for this, and then that will give you one part of the equation. So note this: the first thing to do is to analyze this first triangle. The next thing to do is to analyze this triangle. You're going to get some information. Then the third thing to do is to analyze the torque. So quickly, as I do that, you're going to understand what I mean by that. So let me give a clear explanation to the concept and the assumption we are making before we start analyzing the equation. So first we are assuming that this is a shaft. So it's more like something in this nature. This is a shaft. And so we are assuming that we apply a torque to rotate it, that is to hold this front end and try to rotate it. Now, the second thing is that we are assuming that this end part of the shaft is fixed. So that means if you try to rotate this part of it, this part will not rotate, because this part is fixed. Let me just do this. So let's assume that this part of the shaft is fixed. So if you try to rotate this aspect of it, this end part will not rotate. It only have this part to rotate. Now, let's assume that we take a line from here to here. If you try to rotate it, because this end part is not allowed to rotate, you are going to have some shearing. So as this rotates, it will move from this point down to this point, and you have this line that was straight to go in this direction. Now notice that this is the radius of the circle, and from here to here is the length of the shaft. Next, we are assuming that we apply torque that tends to rotate the shaft. Now, as a result of this torque, there will be some shearing of this material, which is the shaft, and that shearing is, there will be some stress induced in the system, and that stress is represented by tau. But this stress is a shearing stress, and as a result of this stress, we still have a shear strain. So a shear stress here and a shear strain. So this angle here is our shear strain. Now, the angle formed from here to here is what we call the angle of twist, which is theta. So let's go back to our understanding under stress and strain. We know that under elasticity, that the modulus of elasticity is equal to stress all over strain. But looking at this, it's not about whether the shaft is being elongated or reduced, or it's not about the elasticity of the shaft. It's about how resistive it is to torsional application. So if you apply torque to it, how strong is the shaft? How strong is the shaft going to resist that the effect of the torque? And that is modulus of rigidity. How strong the material is to rotational force. So we have that modulus of rigidity is equal to the same concept here. Modulus of rigidity equal to, here is normal stress, but here we have shear stress, which is tau, all over shear strain, which is denoted as this. So when torque is applied to the shaft, it's going to observe a shear stress and a shear strain. So we say that modulus of rigidity is equal to shear stress all over shear strain. Now from here we can say that the shear strain is equal to the shear stress all over the modulus of rigidity. Let's call this our equation 1. So I'm just going to write it here. So we have that the shear stress is equal to the shear strain all over the modulus of rigidity. Let's call this our equation 1. So recall I said the first thing to do is to analyze this triangle, and the second thing to do is to analyze the second triangle, which is this. The information you get will help you to derive this part of the equation. So looking at this triangle, what do we have? We have something in this nature. We have something in this nature where this is the shear strain, and this is O, this is A, this is B. Now notice that from here to here is the length of the shaft. So this is the length of the shaft. So what are we looking for here? We are looking for AB, because the line AB is that's what connects both this triangle and this. So we know from SOHCAHTOA that to get this part, this is the hypotenuse, and this opposite, this adjacent. So we want to get this opposite part of it. So the relationship that we use is opposite over adjacent, and opposite over adjacent has the relationship of tan. So what we have is that tan phi is equal to opposite, that is AB, which is this AB, all over opposite over adjacent, L. Now from this aspect, tan theta, if you pick up your calculator and having that tan theta theta is very small. Let's say theta is 0.001. If we punch out tan 0.001, what you are going to have as your result will be very close to what you put in as theta. So what I mean is that if you have tan theta equals to 0.001, what you are going to get as your answer will be very close to 0.001. So therefore, we say that if the angle of theta is very small, then tan theta is equal to theta. So if tan for here is 5, if tan 5 is almost same thing as 5, you can say that 5 is equal to AB all over L, because tan 5 is same thing as 5. So we just take out tan 5 and put in 5. So from here we can say that we have 5 equal to AB all over L. So AB all over L, the length of the shaft. From here, if you multiply both sides by L, you have 5. If you multiply both sides by L, we have L multiplied by 5 equals to AB all over L multiplied by L. So from this can cancel out. What we have is that the length of the shaft multiplied by 5, which is the shear strain, is equal to AB. Therefore, AB is equal to the length of the shaft multiplied by 5. So let's call this our equation 2. So I'm just going to put it here. So we have that AB is equal to the length of the shaft multiplied by the shear strain. So let's call this equation 2. So we have analyzed it. Remember I said you analyze this triangle, you do the same thing for this, and then lastly you analyze it up. So we are done with this triangle. Let's go to this. So looking at this, what do we have? We have something in this nature where this is C, and this is A, and this is B. So AB, and this is C. This is C. So we have here as our theta. Notice that from here to here is the radius of the shaft. So we have here as arrow. So how do we get AB? It's the same procedure. We have these are opposite over adjacent, which is tan theta is equal to, because it is opposite over adjacent, we are using tan theta equal to AB all over R. So remember I said if tan theta is very small, why we are saying that tan theta and why we are saying theta and phi are very small? In real life scenario, if you try to rotate the shaft, the angle it is going to rotate will be very small. Will be very small. So let's say this was supposed to be the shaft. If you try to rotate it, let's say this was the initial point to. If you try to rotate it, the change will be very small. So theta is very small. So that's why we are assuming that since theta is very small, that tan theta is almost equal to theta. So we have that theta is equal to AB all over R. All over R. So from this we can make AB subject of the equation by multiplying both sides by R. So if we multiply both sides by R, multiplied by this equal to AB all over R multiplied by R. This will cancel this. What we have is that R, which is the radius, multiplied by the angle of twist is equal to AB all over the radius of the shaft. So from here, so from here we can say that AB is equal to the radius of the shaft multiplied by the angle of twist. So let's call this our equation 3. So I have that AB is equal to the radius of the shaft multiplied by the angle of twist. Let's call this our equation 3. So I said first thing to do, analyze this, and to give you the relationship of this part of the equation and this. So let's quickly do that. Looking at equation 2 and equation 3. So let me just write down. From equation 2 and 3. If looking at this, we have AB equals to this and AB equals to this. So therefore this and this, they are equal. So we can say the length of the shaft multiplied by the shear strain is equal to the radius of the shaft multiplied by the angle of twist. So from equation 2 and 3, we can equate both of them. So we have L multiplied by the angle of the shear strain, equal to the radius of the shaft multiplied by the angle of twist. So from here, what next to do is to make the shear strain subject of the equation. So if you make it shear stress subject of the equation, we have shear stress equal to R multiplied by the angle of twist all over L. So we just move this to this part. Now note from equation 1, we said that the shear strain is equal to the shear stress over the modulus of rigidity. So we can take this and put in here. So therefore we have that since shear stress is equal to the shear strain is equal to the shear stress all over the modulus of rigidity, we can put this into this equation. So from this we are replacing this with this. So we have that the shear strain all over the modulus of rigidity is equal to this. So the radius of the shaft multiplied by the angle of twist all over the length of the shaft. So we have R multiplied by this all over the length. So from here we can make shear stress subject of the equation. So we have that this is equal to R multiplied by this all over the length multiplied by G. So we just move this to this part and we have this. And we can rearrange this to say that the shear stress all over, take the radius to this part. So we have the radius, the shear stress all over the radius is equal to modulus of rigidity multiplied by the angle of twist all over the length. So remember I said once you analyze this triangle and this, it's going to give you one part of the equation. So that's what we've done here. So let's call this our equation 5 and this will be equation 6. I'm just going to write it down. So we have equation 5 to be this. So we have shear stress is equal to the radius multiplied by the angle of twist multiplied by modulus of rigidity all over the length. Let's call this our equation 4. And then this is our equation 5. So the shear stress all over R is equal to the modulus of rigidity multiplied by the angle of twist all over the length of the shaft. So these two information gives you this part of the equation. And when you analyze the top, you now have this part of the equation. So let's go further. Let's call this equation 5. So we have successfully analyzed